Listen, here itself. Taking the fixed point, which is at a height h above the Earth's surface, if there is m1, potential energy is m1gh. If there is m2, potential energy is m2gh. m3, potential energy is m3gh. If you want to characterize the gravitational field by giving the potential energy of every point, that potential energy appears to be non-unique. Different masses have different potential energies. Unique thing at this particular point is actually what? GH, which is the standard point for us. At any point in the gravitational field, if I want to define a standard gravitational potential, it is GH. For any mass kept there, it is mgh. Unit mass, potential energy of unit mass is GH. For any mass, m is mgh. Standardizing it, actually. Listen. Like, when the potential energy is GH, G is the weight of unit mass, correct? G is the weight of unit mass. In mechanics, kinetic energy or potential energy are non-negative quantities. The change can be positive or negative. Correct? Correct only. But in electrostatics, because you have negative charge, there is no negative mass in mechanics. Negative spring constant. Because there are negative charges, we talk about negative potential also here. Okay. Electrical potential difference. Between 2 points in the electric field. Where E is the electric field intensity. A and B, let us say. Where E is the electric field intensity, which is the force experienced by mathematically unit positive charge. By definition, when you want to tell, by a small test charge per unit of the charge. Because unit charge is huge. But here we can say it is mathematically also say that unit charge. Is the always work done on unit positive charge, practically to be understood as what? On a small positive test charge per unit of the charge. Against the field force. Work done on the charge against the field force to move it from one point to the other. Defined like this only. given as integral minus of E bar dot dl bar from, let us say, A to B. Call it as VBA. Like G bar dot dl bar, taking M to be equal to 1. Most general case, F bar dot dl bar is now E bar dot dl bar. F is maybe the force on unit mass. Check it once. I'll explain it, don't worry. But because this is also field where charges experience the force. In gravitational field, masses experience the force. Ultimately, when I evaluate VBA, it can be positive or negative. Basic definition is this only, because we basically define it for positive thing. But for a given path in the given field, for a given set of points, it may be negative also. So, listen. At any point in the field, of intensity E bar, field intensity, if unit positive charge, understand it is as small positive test charge per unit of the charge, is moved through a differential vector dl bar, the change in its potential energy, the change in its potential is potential energy only, is equal to dV equal to minus E bar dot dl bar. Minus E bar dot dl bar. Can somebody at least tell why minus I am keeping? Why minus is coming here? Ultimately, the dV can be positive or negative depending upon dl bar. But why minus is coming? Minus E bar dot dl bar, because by definition it is the work done against E bar. Work done against, because of which it is minus E bar dV. And when the object is, when the charge, when it is moved, from A to B along a given path, C, along a given path C, the potential difference, please check it. Very important for us. Difference is what? VB with respect to A, VB minus VA. Ultimately, it is VBA. It is actually potential of B with respect to A. It's like this. You have an object of mass m at a height h. Its potential energy is mgh. If I have a mass of object of mass m at a height h1. If it is moved to a height h2, absolute potential of this is mgh2. But with respect to this position, mgh2 minus h1. This is the amount of work done. Actually, every object of mass m will have zero potential energy in the gravitational field only when it is there at the center of the earth. If it is there on the surface of it, if you remove the something, whatever is there below, it starts going down until it reaches the center where it stops. From there, for it to move, you have to apply the force. Otherwise, it goes to that center and stops there. VBA, potential difference. Actually, this is always VB minus VA equal to minus integral A to B along the, this is actually along the contour C, sorry, path, not contour, curve C. Along C, E bar dot DL bar. 1 point, right? Basic things only we will understand. Everything I will try to get it from gravitational field, whatever we understand directly, and then take it into the electric field also. Listen carefully. For all practical purposes, gravitational field is considered to be conservative. Conservative, because principle of conservation of energy with respect to kinetic and potential energy hold good. Conservative is what was the assumption here. If it loses its potential energy, it gains kinetic energy. Fine. Conservative is actually what? If it is taken from this point to this point, there will be certain amount of change in potential. If I bring it back, total change in potential is what? If delta V is the change in potential in this particular path, positive for sure. Minus delta V will be the change in potential when it is from A to B, delta V. From B to A, minus delta V is the change in potential. Because of which, if it is taken round and then brought back to the same point, there is no change in its potential. Total change in potential is 0. Total change in potential energy is 0. Means what? Listen carefully. For this also, we know that it is delta V. For this also, it is minus delta V. Correct? You agree this? One good thing for us is in a conservative field, please remember this. In a conservative field, the potential difference between 2 points, its gravitational potential difference or electrical potential difference, is only a point function, not the path function. Why? From A to B, whether I go in along path 1 or path 2, or now I will define path 3 up, path 4 up, When I come down along a particular path, if the change in potential is minus delta V, if I go up, the change in potential is plus delta V. Extremely important point if you want to become expert in network analysis, I'm telling you. I'll show that these points are extremely important for us. The potential difference between 2 points in a conservative field is only the point function, not the path function. Along which path you have come from A to P doesn't matter if the field is conservative. That's why in network analysis, if somebody wants you to determine the potential difference between 2 points, in a big network, there can be several paths along which you can start at one point and go to the other point. Because it is not a function of the path followed. A good student will take the path that contains least number of branches between these 2 points, calculate the potential difference. Because it is independent of the path. When the potential difference between A and B is independent of the path followed, when there are several paths along different branches, KVL tells what? Now what is it? If I go around, come back to the same point, what should happen? In one path, if I go from A to B, there is a positive change. B to A, if I come back, there should be an equal amount of negative change, because when I change the direction of it, integral A to B, when I put integral B to A, definitely the value will be minus of the other only. For a given path, definitely when you change the direction of the path, the value of the integral will just become negative of the initial value. This is actually what KVL is. Only because KVL is followed by the networks, potential difference between 2 points is independent of the path followed. Because of which we take only the shortest path and determine the potential difference. In a conservative field, in any conservative field, the potential difference between 2 points, is it clear? Two specific points is only the point function. Which points are of interest matters. Is only the point function where they are. Not the path function. That's why we did not, nobody asked when I initially told if there is an object of mass m at a height h above the Earth's surface. Immediately we told potential energy is mgh. Unknowingly, correct? We told it is mgh. Why immediately we told that it is mgh? Because I don't know whether everybody knew that it is independent of the path followed, only the position matters, because of which it is potential difference. Maybe that point we should insist. Whatever may be the path followed, in this case also, like this also you can come, like this also you can come. If my final position is at a height h, its potential energy is mgh. Somebody would have taken it like this also. Doesn't matter. That's why we will never ask who brought it, in which path it came. We don't worry about it. Its potential is mgh. Its potential energy is mgh. I'm talking about only potential here. Okay? Because in electrical terms, it's only potential, though it is potential energy. Listen now carefully. Is it clear? Is only the point function, not the path function. So, in any conservative field, minus, I know you know this, right? E bar dot dl bar is equal to 0. Along a closed path in the field, if I go round once, initial and terminal points are same in this case, irrespective of, let us say this is A, this is B, this is C, straight away to D. So A again, or it can be D, then back. Whatever may be the closed path that you follow, minus integral E bar dot dl bar is equal to 0 implies integral E bar dot dl bar is equal to 0. This we write as KVL, right? This is V1, this is V2, this is V3, this is V4. Because of the path, it can be positive or negative. Some of the voltages around a loop, around a closed path is equal to 0 is what is integral E bar dot dl bar is equal to 0. And the best example of conservative field is gravitational field. From there we can understand everything. Check it once. In any conservative field, minus integral E bar dot dl bar is equal to 0 implies integral E bar dot dl bar is equal to 0. From this and this, we talk about this as what? It leads to KVL, which says that basically algebraic sum of the voltages around a closed path is equal to 0. One more point I'll just try to put. In the gravitational field only, equipotential surface, you should, if you can please, if you can tell, please tell, okay? Equipotential surface is what? The surface on which everywhere on that particular surface, the potential of a particular object is same, or the potential is same. Then we call it as equipotential surface. Is the surface on which at every point the potential of an object is same. Hey, which is that surface in Earth's gravitational field? In the region where we stand, it is a horizontal surface, correct? But as a whole, it will be a spherical surface, not a perfect sphere that we know. If every point on this surface sorry, yeah, is at the same height h. It's a horizontal surface. At any point on a horizontal surface, the potential of an object is same. Means what? If A and B are 2 points on that surface, integral minus A to B or B to A, G bar dot dl bar or E bar dot dl bar is equal to 0. Why? Why, man?
Potential of A is same as that of B.
Actually, on the surface, it is true because very, very significant point, concentrate. These are all normally you know, but you know, just okay, neglected the statement. When I say that I have a path on this surface, extremely important point for us to go forward and talk about directional derivatives and all is because at each and every point on this surface, gravitational field is perpendicular to it. If I say G bar dot dl bar, if I evaluate, it is everywhere 0 because G bar is in the vertically downward direction, dl bar is in the horizontal plane. 0 because, please tell me, because the gravitational field is along the normal to the surface at each and every point. Due to which G bar dot dl bar itself is equal to 0 at each point. Correct? Normal to the surface means what? Perpendicular to the surface. When you consider dl on the surface, I told you many times there. When a surface is perpendicular to a line, every line that I can draw on that surface is perpendicular to that line. Equipotential surface. Whenever I say that a particular surface is equipotential surface, immediately direction of the field quantity at any point on the surface is along the normal to the surface. Only because the direction of the field is normal to the surface, that surface has become equipotential surface. Where that's what that's what in physics they say. What is the work done by a man carrying suitcase on his head and walking on the level ground? That's what is the case actually. Now, you cannot say this to a porter, no. But because there is no opposition in the direction in which I am moving, along the horizontal direction, if I am moving, there is no opposition at all. Opposition is in the vertical direction. Because of which, physics-wise, the work done by a man carrying suitcase on his head and walking on a level ground is 0. That is what is the case here.